This is water. Two young fish were swimming along one day, and an older fish swam over and said, "Good morning, boys, how's the water?" And then he swam away, and one of the younger fish looked at the other younger fish and said, "What the hell is water?" This is a little story that is told by one of my favorite American authors of the 20th century, David Foster Wallace, who did a commencement address at a university. And his point of his commencement address was the really important lessons they should take away from their experiences were not all the lessons they learned in school, but all the things that are so common in your life that it's just like water to a fish, that it's so common you don't notice it anymore. But sometimes you really need to notice those little things in your life, because sometimes those things are really important. Now, he's talking about just being a better person in general and living your life, but I'm taking his metaphor and stealing it and applying it to software development, because I find that the exact same thing happens on a lot of software projects, that these things that you're so used to, they're just like water, but you take a step back and you realize that something is not quite what it should be. And so my talk here is really in three parts, and each of them conveniently falls under a Greek letter. And so I'll start by talking about mu, which is about friction. When we talk about this in mathematics, this is about a friction. But when we talk about this applied to software, we talk about friction. What we're really talking about here is engineering friction. It's the kind of artificial barriers you create inside your engineering practices in your organization that make things harder than they should be. Ticketing systems are great examples of engineering friction, which makes perfect sense from an organizational standpoint, but from an engineering efficiency standpoint are really a bad idea. One of the things that we really push for in this continuous delivery world is trying to find ways as much as possible to eliminate friction and make sure that all your engineering practices are working together, because people sometimes over-optimize around a particular tool or process and it does harms to others. And I want to give you an example of that that's very common on a lot of projects. Now, you're all familiar with the idea, the concept of continuous integration, but there are really two pieces to the idea of continuous integration. The first is the original practice of continuous integration, which was created by the extreme programming guys. And they created continuous integration because when they put together extreme programming, it was really a reaction to all the different software development processes that were available at the time. All the guys who put together extreme programming were quite experienced and had worked on a lot of software projects, and said that there was no good predictor of project success regardless of which process you picked, because the processes just weren't very good. And so the concept behind extreme programming was, let's forget about all these invented processes and let's just focus on the things that we know have worked well on projects in the past, and we'll just do those push those as far to the extreme as possible. And testing was a good example of that. They've observed that on projects where they were very aggressive about testing, that they had better outcomes. And so the most extreme version of that was test-driven development, which came from the XP guys. But continuous integration was also one of those things, because they observed that on projects where they were more eager to do integration, they had a lot fewer integration-based headaches than on projects where they did it really late. And so what's the most extreme possible version of that? It's this idea of continuous integration, and they gave us this idea, which of course is quite common on software projects now. But we don't really think of this as the practice of continuous integration anymore. We think of this more as the machinery of continuous integration, because we very quickly built really cool machinery to do this stuff for us. And we have continuous integration servers like Cruise Control and Bamboo and Jenkins, etc. But the practice of continuous integration is really still important. And you can boil it down to this idea that everyone commits to the trunk at least once a day. But let me give you a good example of a lot of projects that end up violating this rule. What we're really after here, and the key observation that the extreme programming guys made was this: there are lots of things in the software world that the longer you put them off, they don't just get worse linearly, they get worse exponentially. And integration is one of those things. The longer you put it off, the larger the combination of merge conflicts builds up, and it becomes a more and more horrible problem. And part of the mantra from the XP guys was this idea of bring the pain forward. So let me give you an example of this, a really common engineering practice on a lot of projects. So let's say you have this scenario. You're using some sort of relatively sane version control that has the ability to do trunk-based development like Subversion or Git or Perforce or something like that. And it's decided that there's a new feature that may or may not make it into the next release of our code base. And one of the ways to model this problem is to use branching and version control to handle those in-flight potential new features. This is an engineering practice known as feature branching. And so Professor Plum creates a branch for his new feature, and Reverend Green creates a branch for his new feature, and they start working on their new feature while other developers are still working on things on trunk. Now, both Professor Plum and Reverend Green, being good version control citizens, know that you should periodically pull from the trunk as you work on your little features and do little commits on your branches. And so you can see little pulls from the trunk as time goes by. Maybe a few days go by, a few weeks, maybe a couple of months go by, and it's decided we love Professor Plum's feature. We want it in the next version of our software. And so Professor Plum pushes to trunk and performs what we refer to as a merge ambush on Reverend Green. Because Reverend Green didn't do anything wrong. He just came into work on Monday morning, did SVN up, and now slam. He's got a month's worth of merge conflicts to deal with, which really sucks for Reverend Green. But there's a deeper problem lurking here as well. What happens if, on the very first day of his branch, Reverend Green started making profound changes to the customer class? The very first day of his branch, Professor Plum started making profound changes to the customer class in the opposite direction. They have essentially been coding in isolation from one another for a couple of months, and now Reverend Green has a terrible decision to make. Do I go back and undo all of my changes to customer and reconcile them with Professor Plum? Or, and this is the thing that I'm terrified of, do I just create a second version of the customer class? Because I don't want to go back and redo all that work that I did before, and so now these two will diverge into the future forever. The problem here is that we've traded one engineering practice for another engineering practice, and it was a bad deal. Because what we traded here was feature branching, what we gave up was continuous integration. Because if you're on a feature branch, you're no longer committing all of your changes to the trunk every day, which means that other people can't see your changes, and you have this potential for this awful merge conflict lurking at some point in the future. Notice that if you did actual continuous integration off of those branches, you would never get that really bad merge conflict. But of course, you don't have your in-flight features anymore, so you might as well just do it on trunk. What we actually prefer here is a whole set of practices in the continuous delivery world around this idea of trunk-based development. There are all sorts of engineering techniques you can use here, like feature toggles, which is a really popular technique. We use a feature toggle framework like Toggle Z in the Java world. What that allows you to do is isolate features under toggles, and now Reverend Green and Professor Plum can both start working under toggles, but they're still integrating the trunk, and they can still see each other's changes to shared classes like customer, and can prevent these sort of nasty merge conflict headaches down the road. The strangler pattern is also quite common in this world to handle long-running updates, like I need to update this version of a core library, but I need to do it slowly over time. There are lots of techniques that allow you to stay on trunk and preserve continuous integration without trading it for some other engineering practice. But this really highlights a really bad problem in the software development world, and that meta work is more interesting than work. So how many of you would say, if you really boil it down, you had to describe what you do to your grandmother, it would finally boil down to, I take things off a web page and put them in a relational database, and I take things from a relational database and put them on a web page. For a lot of you, that kind of, when you boil it all down, is the job. And after you've done that 20 or 30 times, it's not very interesting to do that. So you know what developers do when their day job is kind of boring? They invent cool puzzles to solve so that work will be interesting again. And that's exactly where a lot of these branching strategies come from, because meta work is a lot more interesting than work. Building frameworks is way cooler than building things with frameworks, because that's what you have to do for your day job. And so we invent really cool puzzles to solve, and we see a lot of engineering outcomes that are really more just sort of ways to keep from being bored than anything else. This is not a new phenomenon. Back in 1993, Jamie Zawiski wrote a famous blog. He was talking about GNOME, the desktop operating system, in 2003. And he made a note that it seemed like every version of GNOME that came out, he would post bugs for it, and then 2 years later, those bugs would be terminated because a new version of GNOME came out without ever fixing the bugs that came before. And he referred to this style of software development as the cascade of attention deficit teenager style of software development. And he makes the point here that fixing bugs and things like that isn't fun, but building new features is fun, and starting over from scratch is fun, because this time we'll get it done right. But of course, you build just another version of the technical debt that you had before. That's a really, really common thing on lots of projects. So next Greek letter I'm going to talk about is delta, which mathematically talks about change. Now let's talk about change in terms of software, and let's talk about project structure change first. And this is a really bad problem in the US and variably bad in other countries in the world, that when you're young, you get interested in computers, and so you start gravitating to other people who really like computers. And very often those are males, because video games and those sort of things are very male-dominated hobbies. And so you hang out with other people that use computers a lot, and you go to university, and it's a bunch of people that use computers a lot, and it's increasingly more and more male as time goes by. And so you start looking at the mix of genders on projects, and it's overwhelmingly male in most of the world. So look at this famous picture. This is the famous Microsoft founders photo back from 1975. And you'll notice here there are 3 women in this. No, wait, there are 2 women in this picture. And so the ratio of men to women back in the original Microsoft days was 11 men to 2 women. And unfortunately, that ratio is still about the same in the US. There are lots of studies that show that 10% of people on projects, of technical people on projects, are women, or 17% for technology were women, so it's a very, very small number. And this is really bad, and it's bad for more than just the obvious reasons that it's bad. Because there was a study that came out in Harvard a few years ago that shows that when you're doing creative work, if you have at least a few women on the team, the collective IQ of the team gets higher. Not the average IQ, but having a few women on the team actually makes everyone on the team smarter. And up to 50% of women on the team will make the entire team smarter. It has to do with socialization and other sorts of things that women are particularly good at, and men geeks are particularly bad at. And so adding women to your project is the #1 easiest way to make the entire project team work a lot better. So you should emphasize hiring women, because that's the easiest way to raise everybody's productivity, is get half of the people on your project as women. It's really tough, though, because it is such a male-dominated culture that we end up running women away from it, and we should be doing exactly the opposite, because that's actually one of the secrets to getting much higher productivity on projects. So we need to find, as an industry, much better ways to foster diversity. That's a change that we all need to try to support a lot deeper. But let's talk about something from a technical nature, since this is a technical conference. This is another one of those things that is just like water. It's so common you don't even think about it anymore. And the way that we've sold our users on the idea of transactions. Transactions are easy when you have monolithic architectures and you use big, giant industrial strength databases, because most of that work is done for you. And so we've sold users on this idea that the world is somehow transactional. But when you get into things like microservice architectures, this becomes a much bigger deal, because now you're talking about isolated data stores, trying to do distributed transactions and other things like that. What you realize is that transactions actually have a really high architectural cost. But this is one of the things that we've mistakenly sold our users, because most of the world is not actually transactional. One of my colleagues a few years ago very famously made the observation that your favorite coffee shop does not do a 2-phase commit. When you go to your coffee shop, you order coffee, you give them money, and then you walk to another part of the coffee shop and you just trust that some coffee is going to eventually show up. That's eventual consistency. If you had a 2-phase commit, you'd have your money and then have the coffee, and you'd both let go at exactly the same time. That's a 2-phase commit for coffee. But no coffee shop in the world does that. Why? Would that not make you feel better as a coffee buyer if you had that proper 2-phase commit? Well, the reason nobody does that is because it's screamingly inefficient to do that. And so they organize the work a lot better. ATMs also are not transactional because every ATM is designed to work in an offline mode in case its connection to the bank doesn't work anymore. And in fact, the number one example that people always give about transactions are banks, and banks don't actually do transactions because most of your work in your bank is still done at 2 a.m. as a batch job on a mainframe somewhere. That's why things still clear overnight, and so they do auditing and eventual consistency at banks just like we do in the software world. You know, banks existed before computers did, and bank records used to travel on horseback, and there is no two-phase commit when a pony's involved. We've got to get our users away from this idea that transactions are free because it turns out they're very, very expensive from an architectural standpoint. And so what we're looking for much more in this world is ACID versus base, going from ACID more to base, where we're very used to atomic, consistent, isolated, and durable, but now increasingly we have to do base, which is basic availability, soft state, and eventual consistency, because as you start getting more and more distributed and you start getting more and more users that force you to get more and more distribution, you reach a certain point of distribution where you can no longer guarantee all four of the properties of ACID. There's a theorem called the CAP theorem that illustrates this, and there's a formal mathematical proof of this, that once you get to a certain level of distribution, you can't really do ACID anymore anyway. And so we're going to have to get our users used to this idea of eventual consistency. Now, there probably will still be a few things that really do need to be transactional. If you're giving away airline seats and there's a lot of contention, you have to be transactional around that. But we can give up on this in lots and lots of our systems. And in fact, most large sites now don't try to do transactions either because of the CAP theorem. While we're talking about databases, one of the really nice changes we saw a few years ago is the end of the relational database dark ages. When NoSQL came out, we started really thinking about the persistence options we should have on projects. And some really interesting options came out in this space, including some that really kind of fundamentally rethink the way some of the assumptions you make about data, just like water in the ocean. For example, this is a good example of something that fundamentally rethinks the way that you solve problems. This is Datomic, which is a commercial database from the Clojure world, and it is an immutable database server. So think about that for a second. This is a database server that once you put something in it, it's there forever. And so your first thought is, well, it'll just fill up immediately and we'll be all done. But it's not, because it's really a value store, not a data store. So every value you put in it is there, but it can never be deleted. And so, and this is a simplified example, but think about how many times the number 2 is in your relational database. Well, in a Datomic database, you store 2, and then everybody that needs 2 just points to that one because it can never change because everything's immutable. The interesting characteristic of Datomic is that everything is always permanent, so you have a permanent history of everything that happened in the database. You can just go back in time and look at it. But then you have to ask yourself the question, well, why do relational databases do destructive updates? Because when you do an update, you're destroying the value that used to be in that field. And that's potentially valuable trending information. If you had the history of all those changes, you might be able to find out some interesting stuff. But we really can't build relational databases that way because hard drives are really, really expensive, and we really need to maximize our architecture around the cost of hard drive. Oh, wait a minute. That was true 30 years ago when relational databases were designed. And this is a common problem that we run into all the time in the software world. If you look at the evolution of how we think about architecture now, we started from a very small place in the PC world and then immediately started chasing scalability. And so we constantly had to build architectures that support these kind of constraints, these kind of scalability constraints. And so what we ended up with is a bunch of architectures that really emphasize shared resources. This is application servers allow us to share thread pools, share database connections, and build shared architectures so we can get scalability. But just like relational databases, this is built around a constraint that has slowly disappeared over time, because now our biggest problem is not shared resources, it's the kind of coupling that we introduced when we built these kind of architectures. And now as we look at operationalizing these architectures in the DevOps world and the continuous delivery world, these things are really, really hard to make isolated changes in. And so both of these are examples Yesterday's best practice is tomorrow's anti-pattern. We constantly build architectures that solve outdated problems. We build architectures around constraints, and then the constraints melt away, and all we're left with are the constraints that we built into our architectures. So it's worthwhile looking at fundamental things like databases and other tools like that you view as so common, and see if you can rethink how some of those things are working, because that's exactly how advanced microservice architectures like Netflix and Amazon work. Is they've cast away some of these old shared architectures ideas and built these microservice architectures that are really super highly scalable. The other lesson that we learn from continuous delivery in DevOps is that architecture is really abstract until it's operationalized. It's very easy to draw a picture on a whiteboard and say, oh, this is the ORM mapping layer, but that's not realistic, because it's not just an ORM layer, it's Hibernate version something. And when the next version comes out, you have to think about, from an architectural standpoint, how can I support that next version and evolve my architecture to support the actual realities of the deployment, not just the abstractness of the deployment. So the last of these things I want to talk about is Lambda, which is, of course, the signifier for Lambda calculus. And I want to talk a bit about functional programming, because you all now have functional programming available at your fingertips now that Java is finally moved into the functional programming realm. And even if you can't quite move to Java 8 yet, there's some nice libraries in the Java world that will let you do functional stuff. But many of you look at functional programming perhaps and say, well, that gives you code blocks, but I have the command design pattern, so I don't really need that. But it really does make some profound differences in your world. And let me give you some examples of that. And first, I want to talk about evolution just a little bit. And this is a little bit of history about me. Back when I was in university, this was in the mid-1980s, we used a piece of software called Pecan Pascal. Anybody ever hear of Pecan Pascal? This is a variant of UCSD Pascal. There's actually somebody here who's a Pecan Pascal fan. The interesting thing about Pecan Pascal was you could write one set of Pascal source code and it would run on an IBM PC and an Apple IIe, because they had invented this technology that they called a virtual machine. So when you compiled your Pascal program, it compiled to this bytecode stuff, and it ran on this virtual machine thing, and it was slower than Christmas. Even for student projects, it was crazy how slow this was on 1980s era hardware. And so it wasn't a great success, but then a decade later, Java came along with essentially the same kind of architecture, but the hardware had caught up and allowed them to start doing that. The point of this is that over time, we seed more and more stuff to our languages and runtime, and this is a good thing. So over time, we've given up things like memory allocation and garbage collection. Now, functional programming languages let us stop worrying about state and things like command design patterns with closures. I'll show you an example of caching in just a second, where you can now give up caching to the runtime and let it handle all that stuff for you. Even advanced things like concurrency, one of the really cool things about Clojure is that Clojure does for concurrency what Java did for garbage collection, meaning you can write highly concurrent Clojure applications and never worry about deadlocks or synchronization blocks or any of those things, because the language just handles all that busy work for you. And this is really nice, because I did a bunch of work in languages like C++, and I reached a really important conclusion at one point in my life, that life is simply too short for malloc. I don't want to deal with this anymore. This is not the level of debugging that I want to do anymore. I want to work at a much higher level of abstraction, get out of all the plumbing of all the software, and think closer to the problem that I'm trying to solve. All the major languages have functional features now, including Java, including JavaScript. They're all been evolving toward this place, because our runtimes now have enough horsepower to allow you to take advantage of things like map and reduce and filter and all those functional concepts. So our runtimes have now caught up to the point where we have the luxury of working at this higher level. And so let's talk about that for a second and talk about achieving results versus steps. And I will give you a quick example here. I'll actually do a slightly longer example of this in my functional thinking talk later on today. But I've got this little bit of code here. This is actually written in Groovy, which supports some of these functional programming concepts. And what it does is not that important. I'll talk about what it does later today. What I'm interested in here is this sum of factors function right here that basically goes through and sums all the factors for the number that I'm trying to classify. And there's a potential here for a performance bottleneck if I have to classify the same numbers over and over. And so what I want to do is replace this method with one that the first time I see a number, I calculate the sum, and then I cache it so that the next time I want to sum it, I can just return to it. And so that's easy enough to do. This is some groovy code that creates a hash table for the sum cache. And I go in, if it's not already there, then put it in, sum it, put it in there, and then return the that cached value. A lot of you have written code just like this at some point in your life, a little hash table to cache the values of a function. You never have to write that again, because if you have a functional programming language that supports lambdas, this memoization is either built in or it's trivial to add. Now this is memoization in Groovy, where I have this factors of method up here, and as long as it's a pure function, meaning it has no side effects outside of itself, and it doesn't, it just finds the factors of a number, I can come down, there's my sum of factors, I can come down here and say sum of factors is equal to sumFactors.memoize, and now this will automatically cache all those values for me. The caching is built in at the language runtime level rather than me having to handwrite it myself. And this is really nice. This is a good example of a quote that Michael Feathers had when he was making some observations about functional programming. He said that object orientation makes code understandable by encapsulating moving parts. So when you think about the things that you know and love about object-oriented languages, there are lots of different rules and mechanisms for doing information hiding, about scoping, and you can see this and change it. You can see it but not change it. You can't see it at all. So there are lots of moving parts. Functional programming makes code understandable by minimizing moving parts. And this is a good example of getting rid of moving parts, because now I never have to hand write a cache again. That's now built into the function level within my language. And so if I want results cached for a particular function, all I have to do is memoize it. And in fact, in the Groovy world, there are some variations on memoize. Memoize at most this many elements, memoize at least this many elements, so you can actually tune its caching behavior somewhat inside the runtime. I wrote these examples for my book, Functional Thinking, and I tried as hard as I could to write a handwritten cache that outperformed the built-in caching that was built into Groovy. And you know what? I didn't get anywhere close. You know why? Because they cheat. They have access to internal data structures and other things that I don't have access to. And it's probably a good thing that I don't have access to those things, because I would probably mess it up if I started messing around with the internals of how lists and other things worked, or functions and closure blocks work. But I don't have to, because they've built that in the runtime, and now I can just take advantage of that moving forward. Another fundamental change in the functional programming world is how they think about reusing code. Because in the object-oriented programming world, we think about reusing code by building networks of classes that communicate with one another. And so when you solve a particular problem, you have this group of classes together and the way that they communicate with one another. The seminal work in this space is the Design Patterns book, and not surprisingly, every single example in that book has a class diagram in it. And when it comes time to get code reuse, what you do is shave off the reusable bits of this, package it up in some sort of reuse mechanism, and then reuse it somewhere. We don't try to reuse code at quite the same level of granularity in the functional programming world. Because in the functional programming world, the idea is to build these really well optimized machinery around common data structures. And the common data structures are things like maps and sets and lists and those kinds of fundamental data structures. And the idea is that you take data plus code blocks in the form of lambdas, and those code blocks customize the way the machinery works. They plug into the machinery at key places and customize the way that machinery works. And so you pass data structures in, it has some sort of transformation, and then comes out on the other side. Code reuse tends to be at a much finer grained level in this world than in the object-oriented programming world, because you're achieving code reuse more at the function level than you are at the class level. A good example of this is how many XML parsing libraries are there in the Java world? It's got to be more than a dozen in common use, and every single one of those, adhering to the tenets of object-oriented programming, have a really elaborate internal data structures that only they can see. They're completely walled off from the rest of the world. And so even if you have 4 XML parsers, you can't really share any of that internal code because they're all completely encapsulated. Versus the way that Clojure handles XML, because there aren't 12 dozen different frameworks for handling XML in the Clojure world. There's one mechanism that's built into the language that takes XML and mashes it into a well-known map format. And Clojure has well-optimized machinery for working with maps. And so then you can just use the standard functions that are built into the Clojure language that are optimized to use maps to treat XML like maps. And that's a really common characteristic in the functional programming world, is rather than build new data structures, can we mash this new thing into something that we already have tools for and take advantage of the really nice machinery we already have. And finally, let me show you the real advantage of switching to functional programming. Let's say that you have this problem. Within your company, you're given a list of names, and you're now supposed to write a routine that removes single letter entries, capitalizes the first letter, and then returns the whole thing as a comma-separated list. And so here's how you might write this in pre-Lambda Java. Where I go in, loop through all the names, and if I get rid of the single character ones, capitalize them, and then append them all together, and then there's a little code in there that suck off the last extra comma off of the end of that string because it gets one extra one appended onto the end of it. Now, when you look at this problem statement, this code would be a lot clearer if I wrote 3 distinct for loops. One for loop to get rid of the single letter entries, another for loop to capitalize them, and another to return them as a comma-separated list. Because then you could easily see what 3 things were going on. But you never write code like that, do you? Of course not, because you have to iterate through the list 3 times, and you know that's really crazily inefficient, and so you just build it all in one loop. So let's look at what the Lambda version of the same code looks like when you switch it over to Java 8. Because now we can use streams on collections in Java 8, and things get a whole lot nicer. Because now I can do operations like filter and map and collect all on streams. So this filters out the ones that have a name greater than 1. It then maps and capitalizes all the ones that are left. And then the collectors dot joining is smart enough. Collectors dot joining, when you do comma, doesn't put one on the very last one in the list, because that's the common usage, is you want a comma separated list but not the last one, and it automatically is smart enough to do that. This is much nicer because now this reads much closer to the actual problem statement. But let's say that you had the original version of this, and your boss comes by and says, hey, you know, that name cleaning thing is really working great, but we need it to be way more performant, so we need you to make that thing multi-threaded now. So I go, great. Now I've got to pull apart this for loop and start thinking about synchronized blocks and worrying about deadlocks and all those things. But in the Java 8 version, I just switch it over to a parallel stream and I'm all done. Eliminate moving parts. I don't want to think about the plumbing of how concurrency works inside the JVM. Nobody wants to think about that. Fortunately, the guys who wrote the stream library have already thought deeply about it, and they've built a really nice system so that you don't have to worry about it anymore. In fact, the stream library in Java is so sophisticated that if you have a set of operations lined up and it can reorder the operations and make them more efficient without changing the results, it will do so. Because it's smart enough to say, oh, I can do less work if you've got a filter and a map. Let's filter them first so that I don't have to worry about mapping as many elements, and you can actually make it more efficient by doing analysis on what jobs are being doing on streams before you start actually generating values for the streams. The Clojure guys, and Rich Hickey, the guy who created Clojure, resurrected this really awesome archaic English word called complect. And to complect something is to intertwine or weave it together like braids. And this is the source of a lot of our problems in software, is we end up complecting things inadvertently. And in fact, the first Java version of this, pre-Lambdas, that's exactly what we did there. Because we had to worry about the performance of writing our own for loop, we ended up complecting the solution of the problem and making it harder to understand. If you come back to that later, you're going to have to think about that code a little bit and kind of decode it to figure out what it does, versus the Java 8 version is much clearer because it's very very linear, very declarative as to exactly what we're doing. This, it turns out, is the real benefit of moving to functional programming languages. It's not the plumbing kind of stuff like memoization and all those things. It's the ability to operate at a higher level of abstraction. This is one more level up from the plumbing. Notice this is what we've done for the entirety of computer science. We keep building cleaner abstractions over the top of the old abstractions that were there before. For loops were way better than hand coding assembly language to leap from one instruction to another on a counter. And so we built for loops to make that better. Well, this is a better mechanism than that, and now it's built into all of our languages, and now the run times are efficient enough so that this code can operate as efficiently, or in some cases more efficiently, than the underlying imperative code that you try to handwrite. This is this is the nicest characteristic, actually, of functional programming. So when you get back to your office after this conference, try to look for places where you're drowning. And there are all sorts of places where you're doing things that you don't realize anymore. And if you take a step back and observe, you'll notice that you really are kind of drowning in some really crazy things. Now, my day job is as a consultant. And so I get to see a lot of very elaborately broken things out in the world. But there's this thing in the consulting world that we refer to as the out-of-town consultant effect. And the out-of-town consultant effect says that if you rode on an airplane to get to a meeting, then you automatically have more credibility than the people who rode in a car to get to the meeting. Whether you actually have any more knowledge or not, you automatically have more credibility. But there is something valuable about the out-of-town consultant effect, because having someone in that has never seen all of the stuff that you've seen is a really valuable thing. In the book Pragmatic Programmer, they tell a story about how to boil a frog. Apparently, if you want to boil a frog, you can't just throw it in a pot of boiling water because it'll just hop out. But the trick in the Pragmatic Programmer book says if you put it in a pot of cold water and then turn the heat up slowly, he'll cook without realizing it. It turns out that not even frogs are that stupid. A frog will still jump out of the water, but every big company is that stupid. Every one of you is a boiling frog without realizing it, because the insanity has crept in one little atom at a time, and now you have a mountain of it, and it's really hard to see. So when you get back to your office, try to take a step back and really look at all the things that you're doing with a fresh eye and say, is this really the best way to do this, or is this just some weird habit that we've gotten into and we're chasing something that doesn't actually make sense anymore? And maybe So when you get back to your office, try to be your own out-of-town consultant. And maybe when you get back to your office, for just a brief time, you can take flight. Thanks very much for coming. Hope you enjoy the rest of the conference.